someone's going to be watching the whole playlist.
Okay. I'll just title that one, Remembrance of Nancy Parker. She'd be very old now, so I hope she's still around. Hadn't heard anything to the contrary, but it's been many years. Okay, anyhow. Okay, this is the big deal psi matrix. So we're just working an example in the book, okay? And the example in the book that we're looking at is in section 6.5, is it? Okay, whatever section. And it refers back to a previous example where they actually worked all this out. So I'm just working it all out as a review of what we did last time. The process is always the same. And if the matrix is bigger, well, you just get more eigenvalues, and your eigenvectors have a bigger dimension. Okay, well, anyhow, so here's the matrix. Okay, we got the equation y prime equals ay, where y is now a vector function. Okay, and we talked about that last time, so I'm not writing out what the system of equations is, but I'll just say it's just y1 plus 2y2. Y1 prime equals y1 plus 2y2, right? And y2 prime equals 2y1 plus y2, okay? So when we multiply this by the y1, y2 vector, which is the y vector, right? It's got the functions y1, y2, and this has the functions y1 prime, y2 prime, right? So we multiply this matrix by those vectors. The equation looks like this, okay? And the equation becomes the one I just read. Okay, so our premise. And we always want to know what our premise is because everything follows from the premise. And you got to remember the premise or you don't know what you're doing. Okay? Which is, of course, often the case. There's always a limit of what you can understand. Boy, I left out a symbol there. There's a T there. And I did it here too. So apparently I don't know what I'm doing, but actually I do. I just get careless. Okay, premise. Here's the premise. Very much like the premise you use when you're solving a second order or high order equation, you assume you have a solution of the form some multiple of e to the lambda t, or in the case of those we usually use an r instead of a lambda, but still an eigenvalue. So we could have used a lambda. And in physics, we did yesterday, right? With the RLC circuit, we used lambda instead of r. Because I wanted to emphasize the eigenvalue connection. It's real important in physics. And engineering. Which is why you learned linear algebra. Okay. So anyhow, you have this premise. It's not now a constant number multiple of e to the lambda t. It's e to the lambda t times some matrix, okay, that matches a dimension of y, matches a number of equations you've got. Okay, so we take this and we just then plug it into this equation without going through detail. Y prime is clearly lambda e to the lambda t times this, right? Then it's a times this. Well, by rules, e to the lambda t is a constant with respect to the matrix multiplication. We can factor that out. And now we've got lambda e to the lambda t here and e to the lambda t here. The e to the lambda t's divide out, we get this. Which is just then same. Lambda times the AB vector is just lambda times I times the AB vector. Because the AB vector is equal to I times the AB vector. Clearly I is the identity matrix of appropriate dimension. And we have this, which we can then easily rearrange to this form. This has a solution if and only if the determinant of this matrix is 0, because if the determinant isn't 0, the only solution would be AB equals 0. Because if the determinant wasn't 0, we could invert this matrix and multiply it by this and get the only possible solution. Well, the inverse matrix times the 0 vector is going to be the 0 vector. So AB would be 0, and that would be no information at all because we already know that the 0 vector is a solution to the system. but it's a trivial solution. Okay, so we then skip to the determinant of this matrix. We find that it's this, and that has to equal 0, and we very easily factor this. Lambda is 3, or lambda equals -1. If we can't factor it, then we got to use quadratic formula. Okay. And of course, when we have complex solutions, usually it's not something we can find by inspection and using our factoring skills. Okay. We just pretty much have to go to the quadratic formula. And in any real application, you're always going to have to go to the quadratic formula, whether it's complex or not. Because real data never gives you factorable characteristic equations. Okay?
I have a question.
Yeah.
Could you divide out that AB vector, bottom left?
Here?
Yeah. I don't remember exactly how matrix multiplication works. So you could multiply it by the inverse of AB?
You could write multiply by a row vector that's inverse to the AB vector. But the only one that would get rid of that would be the 0 vector. Okay, it's a good question, but it's kind of not along the lines of what we need to see here. I'll come back and talk about it when we get through this. Okay? So anyhow, we have lambda equals 3, lambda equals -1, lambda equals 3, just using our standard invariant technique for solving eigenvalue equations. We get this, just plugging lambda equals 3 here, we get this equation. This equation, the equation we get from the first row, is identical to the equation is a multiple of the equation we get for the second row, because the second row is a multiple of the first row. Okay? So these rows are not linearly independent, and they better not be, because if they were linearly independent, then the determinant of the matrix wouldn't be 0, but it has to be, because if we did this correctly, it must be. Okay? So you got to understand that, and you should, since you saw it a year ago in linear algebra and we're refreshing it. Okay? And also in my experience, people that have had linear algebra have no problem with this. Okay? So, our conclusion is that A equals B, because -A plus -2A plus 2B is 0, so 2A equals 2B and A equals B. So we get this, and then our lambda equals -1 gives us this, which tells us that A's got to equal -B. And we get this. Okay, so if A equals B, well, we're just going to use the simplest AB we can, where A equals B, which is 1, 1. Can't use 0, 0. That's trivial. Okay, simplest non-zero solution would be that. And A equals -B, well, 1, -1 satisfies that, and I think we're comfortable with that. So our fundamental set is this. Okay? Now, I don't want to make anybody go through this to see what the sign matrix is. So I'm going to stop the video. That's just preliminary. Something you can skip if you understand what we did last time.